Alright, what's up guys? It's Physics 2212 Lab 4 bar magnets once again. Um, Introduction. So the purpose is to compare the observed and predicted distances using Biot-Savart laws for on and off magnetic axis magnetic fields. Dipole, whatnot. Fundamental principles. Whoopsie. Magnetic fields versus whatever. Anyways, in the results, um, we're looking for n, and you'll see that later in the calculations, and we're looking for magnetic dipole moment, which you'll also see in the calculations. So the principles, physics principles and equations used, so you can disregard the electrostatic nonsense. That was wrong. Just forgot to change that. Biot-Savart law. So Biot-Savart law is going to relate magnetic field to a point, to a tiny current element. You can see it right here. We've got B equals mu over 4 pi, which is the constant, mu naught, sorry, and then Q V times R over R squared. This is just the charge, the velocity, and then the observation location, obs minus source. Next, we use the magnetic field of a dipole, which is this nice little formula here. It looks at the close circulation of an electric current system. So that's pretty cool. And then the distance dependence formula. So this is just saying that the magnitude of the magnetic field due to a bar magnet falls off with distance. And that's right here. Ln k plus n ln r. And r is the distance. K is the combination of constants in all parameters. So the experimental design and assumptions. First step is to orient the phone correctly. A second step was to find the location. We did this by putting tape on the bar and putting tape when it was like the most, and then you did the thing. So put two pieces of tape to approximate where the magnetometer was. Step 3 to measure the distance between the magnetometer and the bar magnet for on and off axis. So here's our data. You can see we've got our average B, and there's our LNR terms and LNB terms. Here's the off-axis data too. Data's pretty cool. So we basically just put this in a graph here, and we got a nice little graph approximation here. So anyways, for the calculations for this, we can assume B, K, R to the N. B approximately is M mu naught over 4 pi 2N over R cubed. Our end slope, this is another calculation. I used negative 1.5 here, as you can see. And then the y-intercept is negative 12. They're about the same, though. They're pretty close. K is 9.2 times 10 to the negative 7. Mine was 8 point something, 10 to the negative 7. But anyways, so we can plug these things back in, and we can solve for mu. And mu for this calculation was 4.6. Mine was 3.5. Anyways, here's lab pictures. There's the... Oops, sorry, I had a little timer go off. Anyways, sorry, those were the wrong lab pictures actually. Yeah, I don't think we had any pictures for this one because it would just be a magnet. It's lame. Anyways, for the computational model, we made a nice little glow strip model here. You can see these are the moments about the magnetic field about the point. So, it just looks like a basic dipole. It's coming out this end, coming around and in, and same thing here, around. And this little pink arrow is pointing with the field. And if I put a pink arrow here, it would point towards it just follows. It follows exactly what you think it did. That's a pretty cool code. Anyways, possible source of error. So the assumed bar magnet surely acts as a dipole. Many other electronic devices and magnets were present, so testing values can be very off. The exact location of the magnetometer wasn't exactly found as well. So, what if you hadn't oriented your thing for north and had some intermediate angle? Well, pretty easy. Earth's magnetic fields would skew the results. Next, what if you stick two magnets together? Well, the magnetic field would double, but the direction would stay the same because they would be in line. And if they didn't line, they would polarize together. So anyways, computation model's correct. Bar magnets don't exactly work like bar magnets, but it's pretty close. Anyways, thanks.